If you start studying about databases, you will come to know that the B tree is fundamental to indexes in databases. And in fact, you can learn more about them before watching this video. But there is a problem with it. See, B trees are great because they give us nearly O(n) log n read speeds and O(n) log n write speeds. But there is a problem with it. See, when the data coming in is simply too large, or when it's a write heavy database, this O(n) log n write speed might not just cut it. Moreover, we need to understand our disks are not very good at random access, which means reading and writing data from random places on the disk. In the case of B trees, when writing, we need to swap around and move around a lot of data on its nodes, and that's why there will be a lot of random IO, making this writes slower. So to achieve a solution which can help us do scale writes, we must write data on the disk sequentially and in batches. And to do this, we need to first buffer our data somewhere in the memory and then flush it to the disk. That's what our common sense will be saying. For our understanding, let's consider key value database for today's example. So we have incoming key value pairs, and what we will do is we will first store them in an in-memory data structure called a mem table, right? And this mem table is kind of a red-black tree or some kind of a balanced BST, which helps us to keep the keys in a sorted order. But what if there is a mishap and our database goes down? We need to have some method to recover the data, whatever we will lose in which was in memory. So what we do is whenever we add data to the mem table, we also write it on the disk in a file called the write ahead log, right? And this is an append only operation. So we just append the data there, and we use something called direct IO, which means bypassing the operating system and going directly to the disk to write the data. This makes this writing to the log really fast. So we do not need to worry about write speeds right there, right? So and our database goes down, we can recover all the data and we can reconstruct all our database from that log. Cool. Now let's come back to our mem tables. When these mem tables get to a certain size, we take these and we flush them to the disk in something called a SS table. The SS table is composed of many segments which has keys in sorted order. So whenever the mem table becomes full, it reaches a certain size, what we do is we take that and we write it in a new segment file. So we create a new segment file every time we want to flush our mem table data. And the segment files are immutable, which means whenever they are written to, after that, they are never written to again. They're never changed again. Okay, so this can write data very fast to the disk, but how do we read this data? So what we do, let's say we need London. What we will do is we will first search our mem table, and let's say we find it. Okay, good. We will just return the value. Let's say we don't, then we will search all the segment files one by one in a reverse chronological order. That means we will start with the latest one and go upwards. So we will do let's say a binary search here to find our key, and we will return it. And we can do a binary search because, as I said, this data is sorted. But there is a problem. Even if you do binary search, searching all the segment files, doing so much IO on, let's say, a lot of data, this will be extremely slow. And this would, like, we can sacrifice a bit of reading speed because we want to maximize our writing speed. But guys, I mean, this is just unacceptable. Let's think what we can do to avoid this. So what we do next is we take the segment files and divide it into these parts. Let's call them blocks. And we create an in-memory index. And sometimes this index is also stored in disks in some real-life applications. But let's not go into that today. Okay, so what we do in the index is we keep the first key of that block and we put their offset in it, right? So the offset just means the position in the file. So for Las Vegas and Lucknow, we have the offsets. Let's say we need to search London. What we need to do is we need to see where London might come in. And because this is sorted, we can say that it will come somewhere between Las Vegas and Lucknow, right? So we don't need to search the entire length and breadth of the segment file. We just need to search the positions in between them. So we would just search from here to here, right? So we know that this is London, right? And we'll just return that value 900. So we are not searching the whole file, we're just searching a part of it. Now, if I find my data directly in the index, we can just return it. So let's say I just find Las Vegas here and I need Las Vegas as value. So what I do is I see, okay, the offset is 0. I just read this one location and return 200. Cool. So that's how we can increase our reading speeds dramatically. But there is still one more magic trick that we can pull off to make the reads even faster. See, currently, even if we don't have a key in a segment file, we still read its index, we still read some part of it, and this is useless, right? So we use a data structure called a Bloom filter. Now, if you don't know about Bloom filter, I'm not really going into its depth in this video, but you can read more about it. So what it does is we can ask the Bloom filter, and we can, let's say, put some keys or some values or some elements inside a Bloom filter, and we can ask the Bloom filter a question. Does this key or does this element exist in your set? And the Bloom filter might say yes or no. If it says no, we will be certain, 100% certain, that this key does not exist in that set. But if the Bloom filter says yes, then we are not sure, right? If it says yes, then we are not sure that, that might be existing in that set and that might not be existing in that set. In that case, we can just search those values and see if it's existing or not. So this is kind of a probabilistic data structure. In real life, Bloom filters perform really good actually, even though theoretically it might always say yes and be wrong and we end up searching everything. But in real life, these do pretty good. Now, even with all these optimizations, the read speeds would still be slower than some read heavy database like, let's say, Postgres. But this is a trade-off we are making for this specific breed of databases. So let's summarize the read and write flows once more, just for our understanding. So let's say this key comes in, we will first write it to the mem table. We'll also write it to this write ahead log. And when the mem table fills up, we will write it into our SS table, creating a new segment file, and also create the Bloom filter for it. Let's say we need to read something, let's say Lucknow. We would go ahead and ask the mem table. If we don't find it, then we will go ahead to the SS table. If we find it, then we'll just, just return the value. And then check the Bloom filters. Okay, let's first ask this. Do you have my key? It says no. Okay, let's move on. Do you have my key? It says yes, but let's say there is an index for this segment. We search it and we see that this key does not exist. This might happen in a Bloom filter. Okay, let's move on. We ask this Bloom filter, do you have the key? It says yes. And then we go ahead, search its index. We see Lucknow is there. We read that offset and return the value of 102, right? So this is how the read and write flow will work. We have solved a lot of problems, but there is still one more. See, as the data keeps on coming, the segment files will just grow in number. There would be a lot of duplicate keys and the disk space will be consumed more and more. So to solve this, there is a background process running doing compaction. What this does is it takes two files and makes a larger one to reduce the number of files. So this will be sorted, this file will be sorted, the resulting file will also be sorted. Cool. So the compaction would be running as a background process, not on each query or something like that, but it would run as a background process, fixing our files and making the database health for long term even better. Okay, so this is like some basic understanding you got for LSM trees. Now you can read more in the description from the links to dive in deeper. And guys, LSM trees are used in like many modern write heavy databases like Cassandra, RocksDB, all those things. So, okay, leave a like and subscribe to the channel. I will see you in the next video.